All right, so I'm going to go through example 6.4. I sent out an announcement. There were a couple typos in this example as well as example 6.3 that was corrected before the video for that, and also a very minor typo in 6.9. There was a missing pi in an inequality for the range of the initial condition. In this one, um, the changes are basically this 16 here and this pi cubed had to be changed. Basically what I did is I plugged in the wrong value for L, so it gave me a slight variation of this value here. That forces us to change the estimate here and also the estimate here and the conclusion for how big n has to be. Well, let's go ahead and go through this. So we're in model 2. We have a bar of length 4. The constant from the heat equation is 0.5. And remember what that means is this is a number that depends on the density of the material, or the specific heat of the material, which is how much energy you need to introduce to raise the temperature by 1, and also the constant that appears K sub 0 in the heat flux, so how energy flows through. So all those things go into this to create this number 0.5 for this material that we're assuming we're using. So C is 0.5, so C squared is 0.25. So our equation here is this, with a 0.25 for C squared. Our initial temperature distribution is 1 minus x to the 4th for x ranging from 0 to 4 in this case. And so our boundary conditions are fixed temperatures at the ends. So the bar is not insulated at the ends, so heat, if there's a lot more energy in the bar than there would be at the steady state, then there's going to be a lot of heat flowing out. But over time, there could be heat flowing in or out of the ends, depending on how the heat distribution is changing. But in the end, and throughout all of time, the temperature at the left end will be 1, and the temperature at the right end point will be minus 3 degrees. So the idea in this example is we know what the steady state temperature distribution is. It's this line here where we just basically take in this case, the left end temperature is 1, which I don't write, times 4 minus x over 4, and then we add to that the negative 3 times x over 4, and this creates the linear function whose value at the endpoints match the temperature that's constant throughout time. So the idea here is to basically, our solution is going to be that steady state function which does not depend on time, plus the rest of this function which does depend on time, and is the stabilization portion of the function. It will basically go to 0 as t approaches infinity due to the exponential decay factors in all the terms. So as t gets very large, these terms all go to 0 very fast, so the sum converges to 0 uniformly in time. So where these bn's are, what are these b sub n's? We're not computing the Fourier coefficients related to the function f of x, that is our initial temperature distribution, but of f of x minus this s of x. So as 2 over 4 is just our 2 over L, integrate from 0 to L, L is 4. We have our f of x, our initial distribution, minus our steady state distribution, which doesn't depend on time. This is the function whose odd 8 periodic extension we're computing. And again, one of the exercises is for you to explain why this is going to work for us. Why does odd work? Just like in the vibrating string, there was a particular reason why we used odd extensions there. That same reason is why we're using odd extensions for this f of x minus s of x. It's to guarantee that the series will converge uniformly, as long as f of x is differentiable, basically, and its derivative doesn't have like asymptotes or anything too horrible. So we get these, plugging this into our software, we get these coefficients here, which are easily bounded above for each n. The numerator is bounded above by 32. Denominator is just, we keep it as pi cubed, and we see the power is n cubed. So in our formula that we have for these cases which tend to arise in the simple functions that we're using, our constant c is 32 over pi cubed, and our power is p equals 3. So that means that our formula p minus 1 is 2. So that appears in two places. So this power of 1/2 is really 1 over p minus 1. And the 16 over pi cubed is really our 32 divided by pi cubed, but then also divided by p minus 1, or 2. And then it gives us a formula relating the error we want, which will give us a sufficiently large value of n for the number of terms that we need to get a uniform approximation. So in particular, if you plug in epsilon is 0.1, this formula tells us that choosing n equals 8 is good enough. In the previous notes I had 9 because I had a slight error in the computation of b sub n. So let's look at this animation. So again, just going through Maple, you don't have to use it, but this is how you would use it. Again, we introduce the tools that we need to animate things. We define our length as 4, define our c is 0.5, we define our initial temperature distribution function here as 1 minus x squared over 4, and because of our error analysis, we know n equals 8 is good enough. So we just have to define in our formulas here the left temperature, which is just f of 0, our right temperature, which is f of L, which is just f of 4 for this example. We define our s function s, the steady state function, is our line here. We're just plugging in the numbers, tr and tl. And then for the purpose of this program, I just defined f of x minus s of x, and I gave it a name, and I called it capital F. So again, this first part, we'll just this will just output the actual kind of formula we see for the coefficients. So I'm integrating this difference f of x minus s of x, even though I've labeled it as capital F of x. So these are just the sign coefficients for that, the 2 pi odd extension of that function. So that'll give us the formula, and then this loop will actually compute the numerical values of all those for the subscript b sub j for j running from 1 to 8 in this case, which is all we need. And then we define the function u. Again, this isn't u, but it's the approximation of u, where we have the steady state function plus the sine series part up to n equals 8. And then we're going to animate that for t seconds and 100 frames. The default setting is 10 frames per second for the animation. And we'll see what this looks like. And again, the temperature at the endpoints has to remain fixed at those values, 1 and -3 for all time. And that's why the stabilization is towards the steady state distribution, which is a line, a linear function, s of x. So there's our formula we saw in the notes. I just went ahead and distributed this minus sign that's out front. That's the only difference. So there's our function from 0 to 4 of 1 minus x squared over 4. That's the initial temperature distribution. And we're going to notice that it's very difficult to see this animation moving. I'm going to go ahead and hit play. You can see time is passing, and it's very difficult to see much movement in this change in this heat distribution. It's very slow. And there's two reasons for this. The first, most important reason is our C value is a smaller number. So smaller values of this, again, which depend on the material, cause a slower convergence to steady state. The other reason why this is very slow is because our initial temperature distribution, go back to the beginning, which doesn't look much different than what we have after 10 seconds, is already relatively close. I mean, it's visually obviously not a line, but it's relatively close to the line, meaning the curve here is not very curved, which is telling us that the magnitude of the second derivative in x, which appears in the heat equation, are small numbers in magnitude, and therefore, because of the heat equation, the change in time is also slow. So when you have more curvy distributions, that's when you see more rapid stabilization rates. So generally speaking, in the beginning, you get a lot of quick convergence if there's any places on the graph that are very curvy, and then it'll slowly converge as time goes on. The convergence rate basically decreases as you get very close to the steady state. So we can fix this by just changing the material. So instead of using material, which would give us a constant C.5, let's make that bigger. Let's say 2. Let's multiply by 4. So now it's 2. So this will give us a much faster convergence rate. Remember, C had no bearing on our estimates for how many terms we needed, so we can use the same estimates here. So 8 terms is still good. So now we're going to see this will be a lot faster. So we'll actually see it converging to the steady state temperature a little bit better. And now you can see how it's much faster. It's converging to that straight line, S of x. So this is essentially already, after 7 seconds, it looks pretty much like the line S of x, which has the temperature of 1 at the left and the temperature of -3 at the right.